video, I will explain about nmos diode, its small signal model, its output resistance, then methods used for generating constant bias voltage, then ideal current mirror, and then I will explain about the current mirror error due to the channel length modulation. nmos diode, when the gate and drain of the nmos is shorted, it results in nmos diode. So now it is a two-terminal device which consists of source and gate. When we see the transfer characteristics, that is UGS versus the drain current ID, it resembles a diode current. Here VGS equals to VDS. So VDS is always greater than VGS minus VTH, and it is always greater than this minimum voltage required to be in saturation, that is VGS minus VTH, by a value equal to VTH. So the nmos diode is always in saturation. Here is the small signal model of the nmos diode. So VGS is taken, the gate and drain is shorted. From drain to source there is GM times VGS and then RDS, and then we have iode current and UDS voltage. Here UGS equals to UDS, so we can replace the voltage controlled current source by a resistor whose value equals to 1 by GM. So the voltage controlled current source is replaced by 1 by GM, and we have RDS. To find R out, it is nothing but RDS parallel 1 by GM as shown here. So here RDS will be in the range of 10 mega ohms and 1 by GM is a very small value. So R out can be approximated to be 1 by GM. Next, I will talk about different methods used for generating a constant bias voltage, which will be given to the gate of the nmos, so that the gate to source voltage is fixed and the nmos can be used as a constant current source, or which can be used to be given to the gate of the PMOS, so that the gate to source voltage of the PMOS is fixed and the PMOS can be used as a constant current source. First method is using a resistor divider. So here the gate voltage will be equal to UDD into R2 divided by R1 plus R2, which is a fixed voltage. However, to ripple voltage on VDD, the gate voltage will not be constant. There will be ripple on VGOG, and the resistors R1 and R2 are subjected to process variations, temperature variations. Hence, we prefer to use transistors in analog CMOS design to generate the constant gate voltage. So first method is to use a constant current source and a nmos diode. So in this circuit, constant current IRF flows through the nmos diode, that is the drain of the nmos diode. So the current IRF equals to beta by 2 into UGS minus UTH square. IRF is fixed, then an equivalent UGS voltage will be generated. How does it happen? The IRF current initially flows through drain to source and also through drain to gate, and this charges the capacitance CGS to a value equal to CGS naught, such that the entire IRF current can flow through drain to source. So in this configuration, we are able to generate a constant voltage at the gate of the NMOS. So at this point, we are able to generate UGS equals to UGS naught, which is a constant voltage, and this voltage is defined by the IRF current. In the second method, we can use one PMOS diode and one NMOS diode as shown here. So when a PMOS diode and an NMOS diode is used, the current drain current through the PMOS diode will be equal to the drain current through the NMOS diode. So ID1 equals to ID2. Using the equation of drain current in saturation region, beta by 2 UGS1 minus UTS square equals to beta P by 2 UGS2 minus magnitude of VTH square. Assuming that beta m equals to beta P and UTH n equals to magnitude of UTHP, we can cancel the terms, and then it results in UGS1 equal to UGS2. And applying KVL in this loop, we can say that VDD voltage equals to source to drain of 2 plus drain to source of 1. So VDD equals to magnitude of drain to source of 2 plus drain to source of 1. Since drain and gates are shorted, we can write UDD equals to UGS2 plus UGS1. Since we have proved that UGS1 equals to magnitude of UGS2, we can write UDD equals to 2 times UGS1. So UGS1 equals to UDD by 2. So at the gate of the NMOS diode, we have generated a constant voltage given by UDD by 2. The current mirror, take the circuit which generates constant bias voltage and feed the constant bias voltage to an NMOS transistor T2. This results in a current mirror. So we have IREF, which is a constant current source. This current is fed to an NMOS diode. The NMOS diode generates a constant voltage VGS1, which is dependent on the constant current IREF. And the gate of T1 is shorted to gate of T2. So the VGS1 of T1 equals to VGS2 of T2. Hence, the current flowing through I out will be mirrored to that of IREF. Take the current equation through T1, that is drain current through T1. IREF equals to beta naught by 2 W by L of 1 times VGS1 minus VTH the whole square. Current through T2, that is drain current through T2, is given by I out equals to beta naught by 2 W by L of 2 into VGS2 minus VTH the whole square. Divide IREF by I out. Since VGS1 equals to VGS2, this term cancels. Beta naught by 2 cancels, and we get IREF by I out equals to W by L 1 by W by L of 2. If W by L of 1 equals to W by L of 2, we get I out equals to IREF. Current mirror error due to channel length modulation. In the previous case, we assumed that the channel or the length of the transistor is large, So since L is high, lambda was assumed to be 0. Hence, the effect of channel length modulation was not considered. When the transistors are of small length, lambda is more. So it results in the equation IRF, that is the current through T1, equal to beta naught by 2 W by L of 1 into VGS1 minus VDS the whole square into 1 plus lambda 1 VDS1, and the current through drain of T2 equals to I out equals to beta naught by 2 W by L of 2 into VGS minus VTH the whole square into 1 plus lambda 2 VDS2. Here the gates are shorted and the sources are same, that is grounded, so VGS1 equals to VGS2, and let us assume that W by L of 1 equals to W by L of 2. So lambda 1 will be equal to lambda 2, and let VDS2 be smaller than VDS1. So VDS1 equals to VDS2 plus delta. When we divide IRF by Iout, beta naught by 2, W by L terms gets cancelled, VGS minus VTH the whole square term gets cancelled, and we are left with 1 plus lambda into VDS2 plus delta by 1 plus lambda into VDS2. Here we want IRF by Iout to be equal to 1, but here IRF plus Iout equals to 1 plus the error term, which is defined by lambda delta, that is the difference between VDS1 and VDS2. This is called the error term. So in this case, Iout by IRF equals to W by L of 2 by W by L of 1 into 1 plus lambda 2 of VDS2 divided by 1 plus lambda 1 of VDS1.